Hello all and welcome to Vision Unleashed 10 Breakthroughs Shaping the Future of Computer Vision. I'm your host Ram Iyer and today we kick off the episode 1 from pixels to patches. So, over this 10 episode journey, we'll explore the key innovations that have transformed how machines perceive world, from self-attention models to zero-shot segmentations, which are very helpful in medical and healthcare industry. And each installment brings you face to face with the researchers who have made it happen. So I'm thrilled to have with me Dr. Sukant Khurana. So Dr. Sukant Khurana is a leading data scientist and neuroscientist who works in the intersection of neuroscience and AI, and he has also been privileged with the opportunity to work with Nobel laureates. So hi, sir.
Hello, thanks, Ram. It's great to be here, and let's dive into how Vision Transformer have reshaped computer vision.
Yeah, yes, sir, definitely. So first, let's set the stage. So, like before 2020, convolutional neural networks were the gold standards for image classification. We have had a number of models starting from DenseNet, VGG16, ResNet, etc. So they had been the main standard models that had been used for image classification or basically any other image-based applications that we have seen so far. So they basically relied on sliding filters that detect edges, textures, and shapes patch by patch. Then, out of Google research came the Vision Transformer, following the innovation of the transformer models, basically for the language and natural language processing based applications. So, VAT, which treated an image as a sequence of patches, much like how words in a sentences are treated, and applied a pure transformer encoder. So why do you think why did that idea catch on so quickly? Like why did it spark so well so aptly that it became the gold standard right now?
Yeah, transformers excel at modeling relationships across an entire sequence. In language models, each word attends to every other word to build context. VIT borrowed that concept. Instead of convolutions that gradually build global understanding through multiple layers, self attention lets every patch directly see every other patch in one go. Given sufficient training data, the model learns spatial patterns, edges, textures, even semantic structures purely from raw pixels. That's its power.
Yes, sir. So the implementation itself is kind of an elegant one. So first, when an image is inputted into the vision transformer, it gets chopped into a 224 like into a 16 by 16 blocks, and then we flatten each block into a vector, then project it into a higher dimensional embedding space. You prepend a special classification token and you sprinkle in positional information so the model knows where each patch sits. From that point on, it's the same transformer building blocks used in BERT and GPT. Right, sir?
Absolutely. Yeah, that's right. The positional embeddings are crucial because transformers are permutation invariant. Without knowing where patches belong, the model cannot reconstruct spatial layouts. Once you add those, the sequence of tokens flows through layers of multi-head self-attention and simple feed-forward networks. No convolutionals, no pooling, just attention.
Exactly, sir. So, of course, self attention can be heavy, both in database and computational cost based views, but every patch attends to every other patch. So with almost 200 tokens, you have got tens of thousands of pairwise interactions per layer. Yet the VAT authors showed that when retrained on huge datasets like ImageNet 21K or Google's private JFT 300M, the model matched or like almost beat the state of the art CNNs while often using fewer total compute operations. What's your take in that, sir?
Well, the key takeaway is that the data scale could outweigh architectural biases. See, this is very important. With massive labeled image collections, you don't need handcrafted convolutional filters. The transformer learned its own filters. But if your data set is small, pure VIT can underperform. That spurred researchers to introduce hybrid designs and data efficient training strategies.
Exactly, sir. So, I guess the neighborhood biases is one thing that the vision transformers have solved, which was a major problem that had existed in the CNNs. So, moving further, let's talk about those strategies actually. One popular variant in data efficient image transformer or DIT, which uses knowledge distillation. A powerful CNN teacher guides a small VIT student during training, transferring learned representations without extra data. And the result is actually amazing. A transformer that performs strongly even when trained only on a small dataset such as ImageNet 1K. So, on to you.
Yeah. So another approach uh, preserves local structure by grouping neighboring patches before feeding them to the transformer. Models like T2T VIT recursively merge tokens to capture fine-grained details, helping VIT succeed on mid-scale datasets like CIFAR10, right? CIFAR10. And then there is adaptive token selection, token learner, which learns to pick the most informative patches at each layer, drastically cutting computation without losing accuracy. Again, you can see sort of its attention playing its magic, right? By looking at what is the most informative patch. It's like
Yes.
picking a needle in a haystack.
Yes, sir. Exactly. Like as you had rightly mentioned, we have got variants like the T2T VAT and Swin transformers, like for getting the model trained in much of a like kind of a data efficient and computational cost efficient manner. So moving on, like later we had also explored the hybrid architectures, like a mixture of both CNNs and transformer architectures for vision. So the hybrid architectures have also emerged, and some inject convolutional layers early on to capture low-level patterns and then use transformers for higher-level reasoning. So an example of a kind of the hybrid structure that I can remember of is the conv model that had been introduced lately. So these hybrid often achieve the best of both worlds, like they get the sequential kind of patterns and also the neighborhood kind of patterns. So we get both the local and global embeddings together. So the data efficiency and the global context benefits of self-attention is also attained. And at the same time, the neighborhood kind of patterns are also learned by the CNNs. So is like, as you had rightly mentioned, we have got variants like the T2T VAT and Swin transformers, like for getting the model trained in much of a like kind of a data efficient and computational cost efficient manner. So moving on, like later we had also explored the hybrid architectures, like a mixture of both CNNs and transformer architectures for vision. So the hybrid architectures have also emerged, and some inject convolutional layers early on to capture low-level patterns and then use transformers for higher-level reasoning. So an example of a kind of the hybrid structure that I can remember of is the conv model that had been introduced lately. So these hybrid often achieve the best of both worlds, like they get the sequential kind of patterns and also the neighborhood kind of patterns. So we get both the local and global embeddings together. So the data efficiency and the global context benefits of self-attention is also attained. And at the same time, the neighborhood kind of neighborhood kind of patterns are also learned by the CNNs. So is that a kind of more of a helpful method rather than the plain VAT?
Absolutely. I mean, um, it is really, this hybrid is really obviously the next step forward. But it's not just that, right? You have essentially um, this deployment makes a lot of sense, right? Where it is being
Exactly.
deployed. Vision
Exactly.
transformers are already making waves, right? In medical
Yes.
imaging, attention maps highlight suspicious regions in scans, offering both high accuracy and interpretability. In satellite imagery analysis, which is very relevant for border crossings, right? Or
Yes,
climate
sir.
related issues. Global attention helps detect land use changes, environmental shifts, let's say US Mexico border, right? Or
Yeah.
some like smuggling happening through this Starlink network. I mean, these are all amazing applications, and these are possible with this sort of vision transformer and their practical deployment.
Yes, sir. Exactly. Like as you have said, the application part has seen vast and major advancements with the attention mechanism and the transformer models. And mainly as when the interpretability increases with the attention model, the AI models tend to become more trustworthy so that we can inculcate it into our day-to-day lives. So moving on. So basically what I have to say is that I have seen visualizations where attention hits illuminate roads, buildings or tumors in cell images, microscopic images and all, depending on the task. So that transparency builds trust, critical in domains like healthcare or autonomous vehicles, something like the Tesla, which drives on itself. Where understanding why a model made a decision can be so important that it becomes so decisive, such as something like a life and death situation. So like, don't you think that's an important aspect that VAT have brought in?
Absolutely. And the transformer backbone is modular, right?
Yes,
Transforming
sir.
VIT to other tasks is straightforward. For
Absolutely.
segmentation, you attach lightweight decoder. For detection, you stack on a transformer decoder like DETR. This
Exactly.
plug-and-play versatility has given rapid adoption across research and industry.
Exactly, sir. So, I think like for today, it's been a lot of information about VATs and transformers. So, before we wrap up, let's recap the big benefits and challenges you tell a newcomer about. So VAT's global self-attention unlocks powerful context modeling with enough data. It rivals, exceeds CNNs. It's interpretable via attention visualization, and it serves as a flexible foundation for downstream tasks, say it as segmentation or object detection or anything, basically any task that we want. And on the flip side, you need large scale pre-training or clever variants like a small twitching here and there to shine when data is scarce or when the computational cost is scarce. So, and you must manage computational cost smartly as well. So like, I think as of now, these are the major takeaways of this episode.
Yeah, that's a perfect summary. Vision Transformer taught us that attention could replace convolution, and it catalyzed a wave of innovation. Hierarchical transformers, linear complexity attention, hybrid backbones, and a lot more.
Exactly, sir. So like, thank you a lot, sir, for walking us through all that. And so, from a personal view, I had a question like, sir, you being an expert and a pioneer in the field of intersection between neuroscience and AI, you might have always worked with medical data, and you often would have seen data where the annotations are not easily available for medical images. So
Mhm.
that becomes a major challenge for like pre-training the models in a supervised manner. Don't you think that's
Yeah, that's a challenge, obviously. We can address it specifically. What are the challenges of supervised learning, unsupervised learning, and the annotation issue in biology, and not just the annotation issue, wrong annotation issue in biomedical data is a very common problem. And how even transformers are changing it. That's, I think, a whole different episode. We can have a separate discussion on that topic. But you brought in a very relevant question. Okay.
uh, exactly, sir. So, as said before, while the annotation challenge is always there and label data is always scarce in medical imaging, so that calls in for a self-supervised manner of pre-training the models. So, next on Vision Unleashed, we'll dive into self-supervised learning methods, starting from the ElasticNet, and from the contrastive learning, Dino, SimCLR, BYOL, and the other self-supervised kinds of models, which learn powerful representation without any labels. So I hope you won't want to miss it. So thanks for listening.
Thank you.
If you enjoyed today's deep dive, please subscribe, leave a review, and share with your colleague. I'm Ramasaya signing off. So see you in episode 2. Thank you, sir.
Thank you.